Tick-tock. It's a sound you probably hear several times a day, undercutting the silence of an empty room or trickling softly from your wrist. It is the unmistakable rhythm of human experience, the beating heart of the cosmos that marks the unending passage of time. Time dominates nearly every aspect of our lives: when we sleep and wake, when we eat and move, when we harvest, and when things arrive. Everything is drilled to the tune of hours, minutes, and seconds. But how did our ancient ancestors figure out these units? Who created the fundamental concepts of timekeeping, like minutes and seconds? And why are there 60 of them rather than 100? The answers lie deep in ancient history, stretching back to the dawn of human civilization. That is where our journey begins, in this first part of a 2-episode exploration of the mysterious workings of time, the orchestrator of our existence. Time is the indefinite, continuous progression of existence, the events of the past, present, and future as one. On Earth, its unceasing rhythm governs all things, from the cycles of the planet's biosphere to the day-to-day activities of humanity. Our lives exist in constant negotiation with time. Every interaction we have with the world happens within the context of what time it is. But the units we use today, such as 24-hour days divided into 60 minutes and 60 seconds, did not emerge overnight. No single civilization or visionary invented modern timekeeping. Rather, the practice grew from more than 5,000 years of observing the sun, the moon, and the stars. In the beginning, time expressed itself to early humans through natural cycles, day and night, and the changing seasons. But neither offered enough consistent markers for precise tracking. The moon proved a more reliable natural clock, with its bright phases shifting over a cycle of roughly 29.5 days. These phases guided ancient rituals, agricultural cycles, and religious traditions. Even today, the Islamic Hijri calendar follows lunar months of 29 or 30 days. But lunar years fall 10 to 11 days short of a solar year, drifting further over time. As humans transitioned from hunter-gatherer communities to settled agricultural societies, a more accurate way to track the seasons became necessary. Neolithic societies in Europe turned to the sun. By watching where it rose along the horizon, how high it climbed each day, and where it set, they identified patterns. They constructed massive stone structures such as Newgrange and Stonehenge that aligned with sunrise and sunset during the summer and winter solstices, the sun's highest and lowest points in the sky. These events occurred with precise regularity, making them reliable markers for early solar calendars of 365 days. Meanwhile, in Northeast Africa, the ancient Egyptians were developing their own methods for tracking the year. Their survival depended on predicting the annual flooding of the Nile, which replenished the land with fertile soil. Lunar calendars, though useful, proved inaccurate for predicting the floods. So the Egyptians looked to the star Sirius, the brightest in the night sky. Each year, Sirius vanished for about 70 days as it moved too close to the sun's glare. Its reappearance, known as the heliacal rising, coincided almost exactly with the beginning of the Nile's inundation. Believing the star caused the floods, Egyptians built their solar calendar around this event. Their calendar contained 365 days divided into 3 agricultural seasons of 120 days each, with an extra 5 days dedicated to the births of important gods. Around this time, Egyptians were also developing simple portable devices to measure time during the day. These early instruments, also found in China and ancient Iraq, consisted of upright sticks placed in the ground to track the movement of shadows. They allowed people to distinguish morning from afternoon, though they didn't create fixed-length units such as hours. That refinement came much later. In 2013, archaeologists discovered a 3,500-year-old limestone tablet in the Valley of the Kings featuring a hole for a shadow stick and 12 equal segments drawn into a semicircle. It is one of the earliest known sundials, or more accurately, a shadow clock. It divided daylight into 12 parts, and night into 12 more, giving us the earliest known appearance of a 24-hour day. But these hours varied with the seasons, longer in summer and shorter in winter. The Egyptians, focused on seasonal rhythms, did not seek further precision. To find the origins of fixed-length hours, we must look east to ancient Mesopotamia. This region, within modern-day Iraq, birthed a sequence of advanced civilizations that shaped early mathematics and science. The Sumerians, who lived more than 5,000 years ago, developed writing, accounting, legal codes, and calendars. They also devised the sexagesimal, or BASE 60, number system. 60 is a highly divisible number, far more flexible than 10, making it ideal for mathematical operations. The Sumerians also divided circles into 360 degrees, mirroring the number of days in a year as observed through the stars. But at this early stage, these concepts were purely mathematical, not connected to timekeeping. When the Sumerian city-states declined around 2000 BCE, cultural influence shifted to Babylon. The Babylonians inherited Sumerian knowledge, continuing to refine and expand upon it. They took the 360-degree circle and subdivided each degree into 60 arc-minutes, and each arc-minute into 60 arc-seconds, units still used in geometry and astronomy. But they did not yet apply these units to time. These mathematical tools spread to Greece, where Claudius Ptolemy used them in his influential 2nd century treatise on the geocentric model of the cosmos. Translated through Arabic and later Latin sources, these ideas introduced the terms pars minuta prima and pars minuta secunda, the first and second small parts. As mechanical clockmaking emerged in medieval Europe, these minutes and seconds finally migrated from geometry into timekeeping. By the late 13th century, mechanical clocks appeared in European cathedrals, palaces, and city halls. These early devices lacked faces, relying instead on weights and gears that turned a mechanism to ring bells at intervals. The very word, clock, comes from the Latin, clocca, meaning bell. But these clocks were wildly inaccurate, drifting by hours each day. Over time, clock faces emerged, showing hours, lunar phases, and occasionally the position of the sun. Still, measuring minutes with precision remained impossible until the 17th century. The breakthrough came with Dutch astronomer Christiaan Huygens, who used Galileo's studies of pendulums to design the pendulum clock in 1657. Its swinging rod controlled the movement of a weighted escape wheel, producing the familiar tick-tock sound. Huygens' invention reduced daily errors from about 15 minutes to just 1 minute, and later refinements brought accuracy down to a matter of seconds. For 250 years, pendulum clocks formed the backbone of science, astronomy, and daily life. But they were vulnerable to temperature changes and unsuitable for travel, especially as railways expanded during the Industrial Revolution. With trains crossing numerous local time zones, scheduling became chaotic. Each town kept its own local noon, meaning no two regions shared the same time. Railway companies began pushing for standardized time. In 1840, the Great Western Railway adopted London time, based on observations at the Royal Observatory in Greenwich. By the late 1850s, telegraph lines delivered the Greenwich time signal to stations nationwide. In 1880, Greenwich Mean Time became the official national standard, and in 1884, it became the world's prime meridian. The globe was divided into 24 time zones, each spanning 15 degrees of longitude, an international timekeeping system still used today. At the dawn of the 20th century, another leap forward occurred, the invention of the quartz clock in 1927. Quartz crystals vibrate at extremely stable frequencies when electrified, making these clocks far more precise and portable than pendulum clocks. Quartz clocks drift only about 1 second per decade, powering wristwatches, appliances, and countless devices. But even quartz clocks were limited by the imprecise definition of a second, which relied on astronomically derived solar time. Days and years vary slightly in length due to natural fluctuations, making perfect precision impossible. After World War II, scientists sought a new, universal standard. They turned not to the heavens, but to atoms themselves. Atomic clocks measure time using the electromagnetic oscillations of atoms, particularly the transitions between energy states. In 1945, physicist Isidore Isaac Rabi proposed using atomic resonance as a time standard. Early attempts were no better than quartz clocks, but in 1955, British scientists Louis Essen and Jack Perry built the first accurate cesium-133 atomic clock. They measured the frequency of one atomic transition at exactly 9,192,631,770 oscillations per second. In 1967, this definition officially replaced the astronomical second. From that point on, timekeeping entered a new era. With precision reaching a second lost only every 30,000 years, atomic clocks transformed global systems. By the 1990s, accuracy improved further into the millions of years. Today's best atomic clocks would remain within 1 second of perfect time for the entire age of the universe. This precision powers essential technologies such as GPS, which depends on atomic clocks aboard satellites to triangulate exact positions. Atomic clocks are also aboard the International Space Station, where their measurements confirm one of the strangest truths of the universe: time travel, in the form of measurable time dilation resulting from high orbital speeds. And so, in our next episode, we will explore this deeper relationship between time and space, moving beyond human measurement and into the very fabric of reality. For now, thank you for joining this journey, and until next time, I bid you good night.